Thank you very much, Volker. I was going to start by also telling my story about, how we met. And, for sure, what we can say is that at the time, we both had hair. And so that's the basic difference. So he was still a PhD student. I was a young professor. And then, our lives have been intersecting many, many more times. And also it's good that I'm the last speaker of this day, because I have a chance also to say a little bit of what the other speakers said before and relate to what they said. In particular, Manfred was saying we haven't talked about evolution, and basically my talk is talking about software from the viewpoint of software evolution. So basically, these are the things I want to talk about here. First of all, why Agile methods? No much need to tell you a lot about this, but they are there because they intend to support continuous change. But then the next question is, why continuous change? Because there's a lot of uncertainty that permeates the both software development and its operation. Formal methods, in the sense of formal foundations, as Manfred rightly pointed out, why they can help? Because those formal foundations are the way through which we can provide assurances. So what is new in what I'm going to say? I think that basically what I want to say is that these two camps, the camps of Agile methods and the camp that was more on foundations, on formal methods in that sense, basically they have been hostile to each other for all their lives. And I think that actually there's a lot of benefit if they meet. And what I want to discuss is what it means that they meet and point out what I think that needs to be done so that the marriage really gets consummated. So first of all, I want to talk about change, software and change. We know that software undergoes continuous change. As we heard even before, most of the software that is still used today is software that goes back to many years ago and has been continuously changed. So this level of change, I think, is unrivaled by any other technology. There's no technology for which change is such an inherent, distinct factor. Of course, it can be a problem. And actually, it's almost always perceived as a problem. What I want to say is that it is actually an opportunity. And so what I want to talk about here is evolution. So evolution is, a notion that embeds a positive view of change. We are familiar with evolution that describes, the way we are what we are today. And the notion of evolution includes the notion of improvement. I believe that there was an improvement here. And also a notion of adaptation. So both improvement and adaptation. Adaptation to the global environment in which an entity lives. So this is what I believe that is underlying the notion of change for software. So my claim is, I repeat it here, is that the formal methods, which mean the formal foundations of the discipline, can be integrated into the practice of software engineering in a way that we can really turn change into its positive view, which is evolution, in the sense that I mentioned before. Okay, let me go back to discuss with you why change is so quintessential to software. And let me go back to what I would call the basics. There's, to me, a very foundational piece of work that has been done by Zave and Jackson in the area of requirements engineering, in which they do they focus on this distinction between the word and the machine. So the point is that we, software people, what we do is that we build abstract machines, something more abstract than this one that is shown here, which is a very concrete machine. So we build machines, but the reason why we build machines is because we want to achieve something in the real world. So the real world is actually the place where we can find the goals through which the machine satisfies then certain requirements. So goals and requirements are here, and we build the machine to do that. And the way the machine is able to satisfy the goal and the requirements in the real world is under certain assumptions about the behavior of the environment and assuming certain properties that the environment has. So in some sense, the environment, again, according to Jackson and Zave, is what bridges the gap between the machine and the world. So these assumptions and properties that describe the environment, upon which the machine is built, and upon which we can show that the machine satisfies the goal and the requirements in the real world. So to be more concrete, what is the responsibility of the software engineer when the software engineer builds a system? Again, remember this thing. So we have here the machine that we want to build, and let me call S the specification for the machine that we want to build. Let's call R the requirements that we want to satisfy in the real world, and let's call E the assumptions about the behavior of the environment and the properties of the environments that we use to show that the machine that we build actually satisfies the requirements. So what the engineer has to do is to develop a piece of software, and suppose that S indicates describes the specification for the machine. So develop a software S such that, assuming that the environment behaves according to E, satisfaction of R can be assured. That's our goal. And we can even express this in some formal way by saying that, assuming that the environment behaves according to E, and the machine satisfies specification R, then this entails satisfaction of R. So the requirements are satisfied. This is our duty. So when we build the machine, implicitly, we have to be able to do that, to show that we actually satisfy the requirement through our machine under the assumption that the environment in which the machine is embedded behaves according to R. So I call this the dependability argument. Our duty is to build systems that satisfy, that comply with this dependability argument. Now, the difficult thing in our work is that all these three things actually continue to change. Requirements change. The assumptions about the behavior of the environment change, and I will show why. And the machine, as we build it, the act of building the machine is an act through which we build different versions, we change it. So all these three elements are subject to change. And so this makes our life, of course, hard. So changes in the software, yes, changes in the software are there because software development is an explorative activity. Development is evolutionary, so there's change in the way, as we progress. Because the design space is often very large, and so it's exploratory. And we move from incomplete to more complete and stable solutions. So there's change here. There's changes in the requirements. We know that requirements in reality, in most systems, are highly volatile. They change. You have certain requirements today, they may change next year. And what happens is that, the fact that you satisfy certain requirements induce generation of new requirements. So there's a kind of a positive feedback. I want especially to focus on this, changes in the environment. Especially, Manfred was talking here about cyber-physical systems. Especially in systems that deal with the physical world, getting exact understanding of the behavior of the environment in which the software is embedded is hard. And it's actually useful here to distinguish, when we are talking about environment, about two different sources of knowledge that are useful to distinguish. So the environment is characterized by certain properties, and I use the term properties to indicate known laws of the environment that cannot be falsified. So for example, a known law of the environment that cannot be falsified is Newton's laws of motion. So I know that if the software is applying a certain force in my robotic system in a given direction, then somebody will move in that direction, if the force is enough to contrast the friction for the body, okay? So this is a known property. So I know that if I want to move something, I have to exert through some kind of actuator a force in a given direction. What I call assumptions, just for clarity here, is properties of the environment that are uncertain or changeable, which nevertheless we have to make. And I give you examples. For example, if you are designing some kind of interacting system and you want to ensure a certain response time of the system that you are designing, you have to make certain assumptions about the number of transactions per second that are submitted by users, okay? Now, these assumptions are based on your best knowledge of the environment in which the system that you're building will be embedded, but they might be falsified in the future, right? And if they get falsified, your requirements in terms of, let's say, response time that the system should guarantee will be violated. Another example is, for example, in a cyber-physical system, you make certain assumptions about the change rate of certain physical phenomena that you are controlling in some control plant. And it turns out that actually the physical system behaves differently. So there's both uncertainty and changing conditions. So for example, in the case of the user traffic of transactions submitted to your system, it may be that there is a change because suppose that your system is an e-commerce system. There's more transactions because you're getting close to Christmas time, and everybody is buying, things through your e-commerce application. So there's changes in the behavior. So the user profile is changing in an unanticipated way. But when you designed the system, you had made certain assumptions. Okay, so I think that there is a kind of distinction between properties and assumptions in what I'm saying. Another interesting thing is that part of the uncertainty increasingly in the systems that we build is part of the platform. So we build applications that run on virtual platforms like on the cloud, or they use a service architecture. So they use externalized services. And the behavior of the platform, of the externalized services, are subject to change. So this kind of uncertainty in the environment is also affecting increasingly most of the software that we build is affecting the platform on which the software is running. And actually, so this is exactly what I'm saying here. So we are increasingly dealing with multi-owner systems. So we build systems in which the system that we build is based on parts that are not fully under the control of the designer of the system because they are delegated to third parties. It can be the infrastructure, it can be the services that you use, right? So platform as a service, software as a service. And so this is, there is a famous statement by Leslie Lamport that, a distributed system is a system where I can't get my work done because a computer has failed that I never heard of. And this is becoming even more common. My system doesn't work because there's parts. It can be in the platform, it can be in the services that I'm using that I'm not controlling directly, but I made assumptions about their behavior and lead to violation in my requirements. So actually, so here again, there was a discussion before, as a consequence of Manfred's talk about functional, non-functional requirement. I think I basically follow what the same spirit as Manfred. So basically, I have a dependability argument that has to be explicitly stated in terms of what are the requirements that I want to guarantee with my system. And these requirements, they can talk about, the values of the function produced, but also the timing, the probability. It can talk about, all these things. So there's a notion of what is my contract, which is through the requirements that I have to satisfy. And whenever I break this dependability argument that I mentioned before, for me, this is a failure. Okay, so the failure is, and it can go from quality of service to the real service, because these are also important. They may lead to financial losses, penalties, whatever. Okay. Then the other thing that I want to mention here is that I would like to distinguish between evolution and adaptation. I think there's a useful distinction here. Okay, I call adaptation the particular kind of evolution in the software. By the way, I'm saying the software, but I could even say in the system, because my S before can be seen as the software, but depending on the boundary that you establish, it can be the system. Okay, so for me, adaptation is the evolution that is dictated by changes in the environment. So there's changes because of the uncertainty that I had in the first place, or because there's for some reason there is an evolution in time of the environment in which I'm situated, which requires change. So this is adaptation. So the requirements don't change. It's the environment that changes. And in particular, I've been working for a number of years now on the issue of self-adaptation. So self-adaptation means, enable the software to detect the fact that the environment is behaving in a different way than anticipated when it was designed. So understand, detect this, and react automatically. So try as far as you can. So you build the software in a way that the software is able to detect the change and self-adapt to the change. So I will spend a little bit of time starting from a little bit of history of the work that I've been doing in this area for a number of years through as was mentioned before, an ERC research that I got funded. And so, which is what I call the self-adaptation challenge. So, can changes in the machine, in the software, due to changes in the environment, be self-managed at runtime by making the software self-adaptive? So, you know, you've probably seen this picture before. So, to try to respond to this issue, you know, there was this attempt done originally by researchers within IBM, you know, who claimed that, you know, we should be able to build what they called autonomic systems. So what is an autonomic system? An autonomic system is a system that, you know, whenever there's change here in what they call the managed resource, and this is part of the environment, there are some kind of sensors, and take sensors in a very abstract sense. So the software should be able, through sensors, to detect the change. So there's a monitor here, so you monitor for change, you're able to analyze, to plan a reaction, and execute a reaction so that, you know, whenever there is this change, you are able to deal with the changes that you have in the environment. This was a nice picture, but now how can we make this concrete? And in particular, how can we make this based on solid foundations? So how can we make sure that this self-adaptation is done in a way that you actually are able to track the changes in the environment and align to continue to satisfy your requirements? Okay, so, you know, here I will go very fast to tell you basically what, you know, we found during this research on self-adaptive system, because then I want to put this in a global perspective, you know, with agile methods and so on, as I mentioned at the very beginning. So I will go quick. If you're interested in more details about this, we can talk about it. But so let me just tell you, you know, what were the lessons that we learned here. So the lessons that we learned here is that to make systems self-adaptive, you really have to get to the point in which the runtime behavior of the application changes. So we go beyond, you know, the way today we handle that, we manage the runtime execution of a piece of software. So because the runtime for an application has to be able to detect those changes that occur in the environment, which normally an application doesn't do, has to be able to understand, so to reason about whether what you detect that is going on in the environment may lead to a violation of your requirements. And then you have to react accordingly by reconfiguring your application to continue to satisfy the requirements. So basically, the runtime architecture has to be able to do monitor, to analyze, and react. And to do analysis, you need two things. You need to have a model, an abstract model of the application at runtime, and you have to be able to bring formal verification on the model at runtime. So we need, that's why, you know, what I said, we need formal methods to be brought to runtime. And by formal methods, what I mean is the model of the system and the environment must be kept at runtime through some kind of explicit representation. Whenever you detect a change in the environment, you have to be able to update the model of the environment that you have, and you have to verify whenever there is a change in the environment. You have to be able to verify at runtime if your environment, together with the machine, continues to satisfy the requirements. If not, then you trigger adaptation. So adaptation is built on solid foundations, where the solid foundation is a model that precisely describes your system and verification that the properties that you're interested in continue to be satisfied or not. Just to give you very quickly an example, the example is in the again in the framework of a system that you build that uses components that are not under your control. So where there's uncertainty about the behavior of these services, but you who are building your system as a workflow, you guarantee to your user certain properties despite the fact that these change. So you want to be able to continue to satisfy the requirements even if the environment upon which you base your application is subject to changes. So even more specifically, suppose I have a very simple case study in which you are building a e-commerce application. So your e-commerce application is made, does this, supports authentication. Then you search the database of products. You can buy products. Then you can ship products after you're finished. And there's two ways of shipping: an expensive way, which is express, and a normal way, which is cheaper. And then there's checkout. So you pay. There's a payment here. And then you log out. And in gray, what I'm doing here, these are services that you use available on the network. So there's an authentication service for login and logout. There's two shipping services that you're using. And there's a payment service that you're using in your workflow. So you're building a workflow out of pieces that others are providing, and you want to assure to your customer satisfaction of certain requirements. Let's see, which are the requirements? Well, first of all, you want to distinguish between two kinds of customers. Let's say returning customers and new customers. And you want to provide better service to your return customers than your new customers for some reason. And suppose that, just to give an example of two requirements, as you can see here, they are probabilistic. So this is an interface of the whole system with respect to the user, which is expressed by in terms of probability. So you want to say that the probability of success of any transaction here is greater than 0.8. And the probability that, for example, express shipping for a returning customer fails is less than this one. Okay? These are part of your contract. And when you're designing your system, very quickly, you have to make certain assumptions about the services that you're using. Maybe you are just subscribing some contract with external service providers. And you have to make some assumptions about user profiles. Again, when you're designing your system. So for example, user profiles, what is the percentage of normal users versus returning users? Since you want to guarantee different quality of service to these two classes of users, you have to know what is the probability that the user belongs to one class or the other. And here there's a number of those. And then there's probabilities, about assumptions, that express assumptions about the services that you're using. So what is the probability that the login, logout system, the authentication system fails? What is the probability of failure of the shipping services? Okay, so suppose that, so you make these guesses and then you design your system, and your system can be designed as a state machine with probabilities, which actually is a discrete time Markov chain, but that doesn't really matter here. Okay, and these are, this state machine describes what your system does and the transitions with the various probabilities that we have seen before. And then if you take your requirements when you design your system, it may well be, that those requirements are satisfied. Now, what can happen then is that when you install your system, you discover that actually the assumptions that you make about user profiles is not exactly what you assumed. So what happens, for example, if instead of having 0.35 here, you have a different value? Do my requirements, are my requirements satisfied? Maybe yes, maybe not. How can you do this? Well, what you can do is that you monitor all these events that occur in the environment, and by monitoring, you are able to update these probabilities if there is a change in the behavior. And whenever you do an update, you rerun the check whether these requirements are satisfied or not. Okay, so there is a change, you rerun, and if for some reason, and as happened here, if these change, it may happen that your requirements are violated. So if the requirements are violated, then you need to reconfigure at runtime your application, supposedly in a way that you can then satisfy the requirements. So by keeping the model at runtime and doing verification at runtime, you are able to support self-adaptation. So this is why you need those formal foundations to support your adaptation. Now, does this work? So, to do this, you have to be able to make verification at runtime efficient. The reason is that when you are at runtime, you have to be able to adapt at a speed that is compatible with this, let's say, the change rate that you have in the behavior of the environment. If you adapt too slow, then the environment keeps changing and you cannot adapt to what goes on in the environment. So to do this, you have to be able to make verification efficient. So to make verification efficient, actually, so you need to be able in some way to avoid the fact that after any change, you rerun completely your verification. Now, in the specific case that I was referring to before, and I don't want to go into technical details, but basically verification is done through probabilistic model checking. Probabilistic model checking means that you prove on a state machine with probabilities, in this case, a discrete time Markov chain, you can prove that your model satisfies the specification. But if you have to run the model checker on the entire specification every time there is a change, this becomes unfeasible. Okay? So what you want to do is to make verification at runtime incremental. In particular, in this project, we have been working on a particular kind of incremental verification that we called parametric. So where incrementality is described in a parametric way. The meaning is very simple. You have a model, And what can change in the model, instead of representing this with a value, like a probability, you can represent as a variable, okay? And of course, the assumption is that the things in the environment that can change are a limited number of phenomena, okay? If you do this, I'm just trying to be intuitive here. What you can do at design time is to produce an evaluation condition in which you have these variables that you bring to runtime, so that at runtime, when you measure the exact values, you just substitute the values, for example, in that case, the probabilities, to the variables. And you evaluate the formula. So instead of doing the model checking at runtime, what you do is that you have a parametric formula, which in the case of the particular kind of verification that we do here on state machines with probabilities, is a polynomial formula. So what you bring to runtime is a polynomial formula in which you have certain variables, and you simply feed into this formula the values that are given to you by monitoring what goes on in the environment. So the evaluation becomes very efficient. Now, end of the story of what we can do to make systems self-adaptive. After working on this area for a number of years, actually I kind of stepped back and I said, well, the principle of being able to do incremental verification is extremely important. It is necessary if you want to bring verification on the model at runtime to make it efficient, because you need it. But actually, this is a golden principle that can be used throughout the software lifecycle. And so let me put this into a wider perspective. And here, it wasn't planned to be like this, but I am basically referring to the same slide that Bertrand has been using before. So change actually is quintessential. So it's not only at runtime, as we have seen in the case of self-adaptation, but development is a continuous is a continuous incremental explorative activity, which can be done in a change-oriented, agile way. So no need to say more about agility. And again, if there's a couple of things that Bertrand says in his book about the ugly and the good things. So the ugly thing, and he mentioned that before, and I totally agree, is what they call the deprecation of upfront activities. Requirements replaced by use stories, that's what he said. Specification, which is replaced by tests. There's no need to specify a component, for example. This is just defined by the set of test cases that the component has to undergo, or a system has to undergo. Modeling is considered like, a waste of time. So these are what I think is the ugly part. And what I think is the good is the continuous care about assurance, which is not just at the end. So it's continuous. It's throughout the process. So this is very good. Do not wait for a complete system. So on the other hand, so what I would like to say here is that we need to be able to get rid of the ugly and move the good even one step further. So get rid of the ugly means that I believe that we can automate much of the upfront activities so that, for example, models are not something that you throw away, which is useless, but you can derive, actually, implementation from models. So you can automate and you can integrate them, make them useful, you can make them analyzable. Models are not just stupid drawings. They are something that allow you to make predictions, to make analysis. of your system, and from which you can derive an implementation. So we need to be able to automate upfront activities, integrate them and we can, instead of just having testing, we can integrate verification, some higher level of assurance in the process, in the development practice. So, to do this, so in a sense, what I really think that we can do is an integration of development and operation. So the DevOps, again, cited before, the whole DevOps, development and operation, can be founded on foundations. And basically, this focus on verification can be the unified focus of development and operation. But to make this possible, we really need to revisit verification methods in the light of continuous change. So as before, when I was talking about bringing the models, I'm almost getting to the end. As I was saying before, when I was talking about bringing the models at runtime to support self-adaptation, okay, we need to be able to deal with continuous change and make verification efficient. The same focus can be brought also to bring verification into the development process. So what needs to be done? I need, there is one thing. For example, specifications and verification should allow to reason about incomplete specification, partial. So when you develop a system, there's part of the system that you still don't know. So you're developing a portion, and there's part that will be completed later. So you need to be able to support specification and reasoning about the specification, even in the case in which the specification is incomplete. You need to be able then, whenever there is a change, you don't want to consider the change as the production of the new system, okay? And analyze the system after a change as if this is a new system. I would like to do a delta type of reasoning. I reasoned my system before, and now I make this change. What changes in the verification? So I want to make verification incremental. So some work has been done here. For example, to support incomplete partial specifications, basically, if you have a system that is incomplete, when you verify a system, normally what you have a system, you have some kind of model, you have some property, and then you verify, and the answer is yes or no. Okay? Well, actually, if the system is incomplete, it may also mean that you cannot say yes or no, but it's maybe. And if it is maybe, it would be useful if automatically I can be given what should the missing part satisfy. So what are the properties that the missing part that I haven't, that I left unspecified at this stage? What is the property that this has to satisfy? So it would be nice if I am given the proof obligations that I have, for the missing part, so that then I design the missing part and check it against those proof obligations that have been computed for me. So this would be an aid, an example, of what would be an aid to support. But in general, when I'm talking about incremental verification, ideally what I would like to have is, I have a system or a model and a set of properties that my system should meet. Then I have a change, which is a new pair of the system and maybe even the properties. but the system actually, this is very informal. So don't take this plus and this delta as anything formal. I just want to give you an intuitive feeling. So my new system actually is basically the old system with a few changes. So changes are not deleting everything. So they're localized, right? So my new system, and this is normally the way we proceed, in many cases at least. So the new system is like the old system plus a delta, and the new properties are like the old properties plus some delta. So there is a change, plus or minus. Delta can be negative, let's say. So suppose that I have a proof of my system against the property. Then, what I would like, meaning that this is incremental, the proof pi prime of the new system against the new property can be done by just performing a delta of the proof. That's what I want to do. I don't want to redo complete the analysis, but automatically I want to be able to just focus on the part that needs to be done. Okay, so that's the goal. Of course, the assumption is that the delta is easier, more efficient to perform, and most important, that it explains to me what the change is, what is the effect, the nature of the change. So if we need to go in this direction, I think that this is what we need to merge the formal foundations coming from the formal methods into the development process. We need to be able to revisit verification for logics, for models, for various kinds of logic, and so on and so forth. So getting to the end. So what I would like to see in the future is something that I try to display in this picture. So here is the real world. In the real world, we have the requirements, and we have the laws and the assumptions about the environment. Okay? Now, here is this guy is the developer, so a human who is providing systems. So what this guy does is that there's an initial design, let's say. The design produces a model for the requirements, for the environment properties, for the environment assumptions, and for the machine that is to be built. And then here, there's a dev time iteration. Here, I do this in a continuous iterative way. And this is verification driven, as I'm saying here. Now, once I'm done, I suppose here there is a kind of systematic derivation of the implementation from the model. So a model-driven approach. In the end, what I have is an executable, where the executable is what we normally see as an executable, but also has a part that is monitor and runtime verifier. So what happens now is that at runtime, I have an ops time iteration here, which is self-adaptation. So if by monitoring the environment, if I discover that my verifier discovers that my system doesn't satisfy the requirements, so the system self-adapts. So there was a cycle up there, there's a new cycle down here. But then, what happens is that in many cases, the system cannot self-adapt. Okay, so, there's cases in which, the system that I initially built is not able to reconfigure its behavior to continue to meet the requirements, or the requirements change. So what happens? Okay, so what happens in this case, actually, there's two other cycles here, which span dev and ops. So from ops, so for example, if the runtime monitor and verifier here discovers that no self-adaptation can go on, the end user up there is involved in making changes that the system itself was unable to make. At the same time, if the requirements change here, there's a cycle from the existing delivered system back to development. So there's an external development cycle. So you have all these cycles, development and runtime, they they are there, and the distinction, between development time and runtime, actually, there is a distinction, but they are handled in a uniform manner and driven by verification. So basically, that's the end. Are we there? I think that most of, let's say, the theory behind this is there, but we need to embed this in tools. So a lot has been done in theory, but we need to, and to do this, to make this really go into practice, I think that the two camps, the formal foundations, formal models, and the practitioners, active in DevOps, they have to work together. So this is the end of it. I hope that we can get to this stage. This is just to say that much of this work, as I said, has been done in the context of this project, which was on self-adaptation. Some people, actually there's even someone here in this audience who has been part of this team. So that's the end of it. If you have any questions, I'll be happy to take them.
Carlo, thank you very much. So finally we made it. We had some Greek letters on our slides. Huh? Right. Questions about Greek letters or other terms? Over there? Yeah.
I liked the theories and I also liked the example, but can you bring that together? So we had this example with the web shop and the changing conditions, and how would the system self-adapt here? Is that possible, or is that one of the cases where the self-adaptation is not possible and we have to redevelop?
Well, actually, I only covered a part of the whole story, which is up to the detection. So depending, on how you designed your system, you may be able or not be able to reconfigure. So depending on the components that you have produced so far, it may be that the existing agglomeration of components that you have cannot satisfy the requirements, or you can find, and I haven't talked about how you do this, but there's a way that supports also this part. It may be that in fact you discover that there is a configuration that you can apply to your system that brings the system in a situation in which you continue to satisfy the requirements. Okay?
Yes.
Am I on? Okay. So I think when you say towards a happy marriage, formal methods in Agile, there's one piece of the story missing or not well emphasized. You have to interact with the customer or even end users, and they will probably not understand the Markov chains, or if it's anything like what we saw in the previous talk. But they will ask, so, this looks nice, but now can my system do this and that? And you have to be able to demonstrate this, and also maybe if this and that use case would violate something that was a requirement before, you have to say, no, it cannot, because you told me before it shouldn't do this and that. So I think, and then there's the other part. In Agile, one key is to refactor, and you have to also be able to easily change, refine, and refactor the specifications. So I think there are also very important challenges in order to make this a happy marriage.
Yes, Joel, I agree. So, of course, you cannot expect your end user to understand your requirements if you specify your requirements in terms of probabilistic CTL or whatever, some kind of formal notation. But but there is also a lot of work, there in terms of, let's say, natural language-based patterns that you can use, which can help bridge the gap between a user-oriented description and the formal description. Well, some people here has been working on on this issue. You cannot expect the end user to understand perhaps your formal models. But on the other hand, actually, for example, in this particular case, the formal model is not that complicated. Manfred was arguing that, providing a state machine is something that, maybe not the end user, but, a software engineer can understand. And in this case, there's, state machines with probabilities associated to the links in the case of my discrete time Markov chains. So, yes, so there's a gap there, but, I think that, there's ways to go in this direction and make the approach possible in any case. I think you maybe had another part of your question? Refactoring. Well, yeah, yes, and of course, the refactoring is part of the picture. What I'm claiming is that, for example, if you have a runtime architecture that is able to do monitoring of what goes on in the environment, actually this is also something that provides very useful information that can be passed also to the user, the human, who is responsible for new versions of the system. So independent of the fact that this is necessary to drive the self-adaptation, the ability to to monitor what goes on in the environment and feedback information about the behavior of the environment to the external user can provide useful information to support also refactoring.
Carlo, thank you very much. Once again.
Thank you.